Okay, welcome everybody. We finished our discussion of solving non-homogeneous constant coefficients yesterday. And so today I wanted to talk about what to do when we have variable coefficients. So we could talk about this in general for like an nth order equation, but let's just give a particular example here, a second order equation. So let's just look at the second order case. So let's say we have something like this. Y double prime plus, we'll say A sub 1 of t y prime plus A sub 2 of t y is equal to f of t. So it's non-homogeneous and variable coefficients. Alright, so now, like if you wanted to write like an L operator that gives you this, this would be d squared plus a1 of td plus a2 of t. This clearly is not a constant coefficient operator, right? This is definitely variable coefficients, right? So rewriting this equation in a simpler form, it would be Ly is equal to f of t. Here, a lot of times you're just going to see it written out fully like this. Okay. That is, even when we're talking about it generally, I'll write it out like that usually. So, for a non-homogeneous equation that had constant coefficients, we had two main methods that we used to find a particular solution, right? So, and this particular solution allowed us to find a general solution. So, the question is, so this is still linear, right? So this is linear, variable coefficient. So it's still linear, but it's variable coefficients and it's non-homogeneous, right? Okay, so keeping track of all these qualities it has. Now, the general solution to this thing is still going to be y of t, which is the homogeneous solution, plus a particular solution. Now, what do I mean by this? Well, this homogeneous solution, right, where y sub h of t is the general solution to the associated homogeneous problem, y double prime plus a1t y prime plus a2ty is equal to 0, right? And y sub p of t is a particular solution to this thing. Okay. And the reason why this form of the general solution is the same is because of the linearity of this. So it's the linearity that gives you that your general solution can be written as homogeneous solution plus particular solution. Okay, and we're still in the linear case, right? Even if we have variable coefficients. Okay, now what's the process here? So before, with key identities and undetermined coefficients, which were our two methods for dealing with a non-homogeneous constant coefficient equation, knowing this was nice because the homogeneous solution was easy to find, because we spent a couple of days writing out the general solution to homogeneous equations like this, where you had constant coefficients. And all of that came from the characteristic polynomial stuff, right? That was what we did. And then the undetermined coefficients and key identity stuff actually was what told us how to find this particular solution. Okay. But in this case, there's a slight issue here, right? So in the case of using undetermined coefficients or key identities, finding the homogeneous solution was really easy, right? Like if in terms of the total amount of work on the problem, right, writing out the homogeneous solution was maybe like 5% of the work, where using key identities or undetermined coefficients to find the particular solution was like 90 to 95% of the work, right? But here, something's a little different because we were able to use all this stuff with the characteristic polynomial to find this thing in the previous case, right, when we had constant coefficients. We can't do that now, okay? So there is a slight problem with this. Saying y sub h is the general solution to this variable coefficient homogeneous equation. So all we have to do is to solve a variable coefficient homogeneous, say, second order equation like this. There's a slight problem. So here's a fact. In this course, we have no general way of solving this. Okay. It's because one doesn't exist. That's why. It's not just that, we'll get to it eventually. It's because there's not one. Okay. This has to be of a very special form for there to exist general ways of dealing with it. Okay. So, for instance, if both of these are just constants, then we know how to do it. And you might laugh at that because technically the constant coefficient case, right, is a special case of the variable coefficient case, right? So imagine a variable coefficient problem like this where actually these functions of t are just constant functions. Well, then you're in the constant coefficient case, and so the constant coefficient case is necessarily a special case of this. It sits inside variable coefficients, right? Variable coefficients are more general. So obviously in that case we know there are some other special types of variable coefficient equations that I remember when I took differential equations for the first time, we had to memorize a couple of these. So Cauchy-Euler equations are a special kind of these variable coefficient homogeneous equations, and those have a particular form that basically if you don't remember the derivation, you just have to memorize the form. There was a couple of different types of these sorts of equations we kind of had to memorize, but we're not going to do anything like that in this course because, and again, like I said, because there's no general way of solving this. So what does that mean? If there's no general way of solving this, then how are you going to be able to find y sub h? So typically, you will be given y sub h of t, or will be able to find it in a way you know. We'll see what I'm talking about here in a little bit. Okay. Really what I'm talking about is the case when this is actually these are constant coefficients. So these two functions are actually just constants. Okay, that's what I mean here. And you might think it's a little silly for that to be something that you would do with what's supposed to be a variable coefficients problem. But I'll show you how actually one of our main uses of this variable coefficients method is going to be to solve constant coefficient equations that we couldn't otherwise, right? So remember, we had a key restriction with constant coefficient non-homogeneous equations, and it's that the right-hand side function had to be in characteristic form. So it's going to turn out the method that we go through here does not have that restriction. This right-hand side function can be whatever. Okay, and so if you apply this, what we're going to do, to the special case when a1 and a2 are constant and f of t is something that's not in characteristic form, you're going to be able to do it. So that's something you weren't able to do before. Okay, so let's say that I'm given y sub h of t, or otherwise I found it, right, through divine inspiration, or I just happen to know what it is instinctively. And I've checked and verified, and yep, y sub h of t solves the homogeneous equation here. How do I find y sub p of t? So let's say that is the step I'm at. Let me just restate that. So say I know y sub h of t, which I'll go ahead and write as c1 y1 of t plus c2 y2 of t, right? This is a second order equation. I'll just bring this back real quick. This is a second order equation, so the associated homogeneous solution is second order equation, looks like this. So then I know, because this is linear, that this general solution is going to look like this, where y1 and y2 are two linearly independent solutions, so they form a fundamental solution set. So say I know this. How do I find the particular solution? Right, and by the usual thing, if I find the particular solution, I'm done. I've found the general solution of this thing, since the general solution is just homogeneous part plus particular solution. So how do I find the particular solution here? So the method that I use to do this is called variation of parameters. And once I explain to you the name, then you won't forget how this goes. Okay. So, variation of parameters means that I am taking parameters and varying them, right? So, what is the idea? The idea is to let y sub p of t be equal to u1 of t, y1 of t, plus u2 of t, y2 of t. Then determine u1 of t and u2 of t. Now, why would this aptly be described as variation of parameters, or me varying parameters? So, what I have done here is, it's like I've taken the homogeneous part, and instead of having these parameters, these arbitrary constants c1, c2 that parameterize two infinite families of solutions here, I turn those parameters, those constants, into functions of t. Right? So I allow them to vary with respect to t. They're no longer constants. Okay. So this is what I do. Now I can do this, plug this in, and see what these things should be. I'm not going to go through the whole derivation. If you want to see how this works, this is page 4 in chapter 2. So this is chapter 2, section 7. So page 4 in chapter 2, section 7. If you want to see the derivation of this from the online notes. So that's where that comes from. All right. So then what do I end up getting out of this? So because of a few assumptions I've made, like the fact that y1 and y2 are linearly independent. Well, if y1 and y2 are linearly independent, what does that mean? That means their Wronskian is non-zero everywhere that matters, right? So that's, again, going back to the general theory stuff. I have a linearly independent set of solutions, or a fundamental solution set. So the Wronskian of y1 and y2 is not zero. This is going to play in a crucial way here, because it turns out, and this is the part that you just know, okay, so that I don't have to go through this derivation. It turns out that if I take this and I plug this into the differential equation in question and simplify everything, it turns out that I can solve for u1 and u2. And if I do that, u1 of t is what? u1 of t is minus the integral of y2 of t, f of t, over the Wronskian of y1, y2 of t, dt. And u2 of t is the integral of y1 of t, f of t, times the Wronskian of y1, y2 of t, dt. Where the y1 and y2 are the parts of the homogeneous solution, the Wronskian, well, you know how to compute the Wronskian of two solutions to a differential equation. And f of t is that right-hand side function, the forcing function, in your differential equation. Notice a1 and a2 do not show up here explicitly, right? So, of course, a1 and a2 matter. The different a1 and a2 will yield different y1 and y2s, but just to illustrate that a1 and a2 do not actually explicitly show up in these formulas, right? Okay. So this is variation of parameters. Now, like I said, this may seem like it comes out of nowhere, but if you look at that derivation that I mentioned in the online notes, you can actually see how this is derived. We're going to see a little bit later, there's an alternative formulation of this. So I'm going to introduce something called Green's functions, and you'll see that this can be reformulated in terms of Green's functions as well. I don't know that that will be more or less illuminating than just seeing it like this, but it turns out that this process is actually extremely general and has very little restrictions. So when can I use this? Well, whenever I have an equation like this. Non-homogeneous variable coefficients, no restriction on f. Right? No restriction on f. So as long as I have something that, by the existence and uniqueness theorem guarantees I have, the existence of a solution and the existence of a unique solution for an IVP that looks something like this, I can use this. Now, of course, as with all of these things, I'm not guaranteeing that you can actually compute these integrals explicitly, right, in a closed form. So maybe this is kind of as far as you go. But in this class, we're going to only deal with problems where we can actually explicitly compute these. So that's the deal. The point, though, is that this can be applied whenever. So unlike undetermined coefficients and key identities, where I have to worry not only that it's constant coefficient linear, but I also have to worry that the right-hand side is in characteristic form. There's no restriction here like that. Okay, so all I need is that this to be a linear variable coefficients, right? That's why we're doing this. And then that right-hand side function can be whatever. Okay, so how does this work? Let's take a look. So let's see how this process works. Okay. So here's an example. Find a general solution of the equation y double prime plus y is equal to secant of t. What's the first thing you notice about this? Note. So of course this is linear. All these are going to be right. We're not going to be able to solve higher order nonlinear stuff. So note, this is actually constant coefficient. So this is a constant coefficient equation. Right? What that means is that this step, right, finding my homogeneous part, i.e. the solution to this, is going to be doable for me because this is a constant coefficient equation. Of course, constant coefficient equation is a special case of variable coefficients. So of course I can apply this, right? If I can apply something for variable coefficients where those coefficients are allowed to be any function, then of course it works for when the function is just a constant function. Right? Okay. So, that's good news, and I'll do that quickly. Note the other thing, right? Why is this something I couldn't have done with undetermined coefficients or key identities? Well, this is not in characteristic form. So why am I repeatedly just going over this? I'm saying the same stuff. I'm repeating myself over and over and over again, making such a big deal out of all this stuff. It's because on an exam, on your upcoming exam, on future homeworks, future exams, projects, that kind of thing, on all those, you're not going to be told what to do typically. So typically I'm never going to say, so this recent homework that I assigned you is the only exception basically, just because I wanted you to have practice with it. But in general, you are going to be given a bunch of equations and told to solve them. That's it. And I'm not going to tell you anything. Right? So I'm not going to say use variation of parameters to do this. Use undetermined coefficients to do this. I'm not going to say anything. So it's going to be entirely up to you to figure out what you have to use to do this. So you have to look at an equation like this, say, okay, constant coefficient, so anything's on the table. Oh, right-hand side, not in characteristic form, that tells me exactly what I have to do, right? That tells me exactly what I have to do. I have to use variation of parameters because undetermined coefficients, key identities, cannot deal with something that's not in characteristic form. Unless, of course, it's in composite characteristic form. But that's not the case here, right? This is just flat out not in characteristic form. Okay? So that's why I'm going over this over and over and over again, because typically you're going to have to figure out what to do on your own. Okay? And you're not going to be given any hint or direction as to what to do. You're just going to be given the equation. Okay. Now you might be saying to yourself, wait though, if I can apply variation of parameters to this, that's not in characteristic form, couldn't I apply variation of parameters to, say, something that was in characteristic form? So here's an aside. Technically, you can always use variation of parameters. Now, you might say, well, that's great. If I could always use variation of parameters, then why wouldn't I do that? Variation of parameters is typically not as nice as the others in a lot of cases. So in a lot of cases, always defaulting to variation of parameters would be less efficient because the amount of work you would have to do would actually be more with variation of parameters, and the computations might be harder. But the point is, yes, you can always use variation of parameters. So this is similar to, it's like solving a quadratic, right? Like you prefer to factor the quadratic just because that's an easy way to read off the roots. But of course, you could always use the quadratic formula, right? Nothing is stopping you from using the quadratic formula every single time and never even attempting to factor something, right? You can always do that. So it's a bit like that, right? It's like if you see how something factors, clearly that's better, that's quicker, but the quadratic formula will always work. So even though it might take you longer, it will always work. And of course, for some polynomials, you have to use the quadratic formula, right? There's no other way to find it because you can't factor. So it's a bit like that, right? But you can always use variation of parameters. Okay. Here we're forced into it, though. So here it's not like we really had a choice in the matter. We're actually forced into it. And so what do I want to do here? Okay, so first, in order to do variation of parameters, I need to solve the homogeneous problem. In this case, because it's constant coefficient equation, I can actually solve the homogeneous problem, right? So the associated homogeneous problem in this case is y double prime plus y is equal to 0. Okay, so the characteristic polynomial, of course, is z squared plus 1, which has roots plus minus I. So it has roots plus minus I. So what's its homogeneous solution? Or what is the general solution to this homogeneous equation? Well, C1 cosine t plus C2 sine t. Right? That's just directly from, there's the roots, so this is the form that it takes. Now, if that's what we've said, then this is our y1, and this is our y2 in preparation for what we're going to do with variation of parameters. All right, so what do I need? Let's look. So my particular solution looks like this. Okay, so a particular solution looks like this, where u1 is this integral and u2 is this integral. Now I found y1 and y2. F is secant t. I can go ahead and write that out. Right, f of t is secant of t here. So then the only other thing I need here is the Wronskian of y1, y2. All right, so let's do that. So what's the Wronskian of y1, y2? Remember, this is determinant. If you have an issue remembering what direction this goes, this is the determinant of the matrix that has y1, y2 as its first row, and then y1 prime, y2 prime. So this is y1, y2 prime minus y2, y1 prime. Okay, so what is this? This is y1 is cosine t, so this is cosine t times y2 prime, which is also cosine t, minus y2, which is sine t, minus y1 prime, which is minus sine t. Hey, this is cosine squared t plus sine squared t, which is just 1. I'm pretty happy with that. Right, so that makes this particularly nice. Okay, so my particular solution is u1 of t, y1 of t, plus u2 of t, y2 of t, where u1 of t is, just to remind you, minus the integral of y2 of t f of t over the Wronskian dt. u2 is the integral of y1 of t f of t over the Wronskian times dt. So this is minus the integral of y2, which is sine t, times f of t, which is secant t, right, over the Wronskian, which is 1. dt. Well, what is this? This is equal to minus the integral. The secant of t is 1 over the cosine. So this is really sine over cosine, or tan t dt. Well, you could have left it as sine over cosine if you really wanted to and done substitution, or you can just remember what the integral of tan t is. So what is this? This would be, so I already have the minus here, so I'm good to go with that. This is log of absolute value of cosine t. Okay, technically like plus a constant of integration. I'm going to leave that off here, and then I'm going to show how actually you could be more efficient by having the constant of integration here and rewriting this in a slightly different way. This is not a big deal, though. So there it is. Like I said, technically there's a constant of integration that shows up here. Okay, so that's what U1 is. So U2 of t is the integral of, so remember this is y1 times f over the Wronskian. So y1 is cosine t times secant t over 1 dt. Cosine times secant t, though, that's just 1, because secant t is 1 over cosine. So cosine t times 1 over cosine t, that's just 1 over 1 is 1. So this is just t, right? So here is my particular solution with U1 and U2 plugged in here. So my general solution is y of t, which is the homogeneous part plus the particular solution. But what that is homogeneous part is C1 cosine t plus C2 sine t plus log of absolute value of cosine t times y1, which is cosine t. Right, so it's log cosine t times cosine t plus t times sine t. Okay. So there's our general solution. Now, I mentioned something about these constants of integration and me just ignoring them here. How can I do that? Well, it's because I was writing the general solution this way. It turns out those constants of integration show up here as the C1, C2. What do I mean by that? So what I could do here is I could actually include in the constants of integration. And then instead of writing the particular solution as U1, Y1 plus U2, Y2, I could actually write the general solution. Y of t is U1 of t, Y1 of t, plus U2t, Y2 of t. Right? And now U1 is log cosine t plus C1. U2 is t plus C2. So what goes here is, log cosine. Maybe I'll write it. I'm going to write it on the next page so that I actually have room. So what does this become if I just copy this over? This would, so y of t would be log absolute value of cosine t plus C1 times y1 of t, which is cosine t, plus t plus ct, or c sub 2 times sine t. But notice, if I rearrange these, this is C1 cosine t plus C2 sine t plus log absolute value of cosine t times cosine t plus t times sine t. So this is exactly the same thing. Right? So you can do that either way you want to. It really doesn't matter, right? Literally, it's the same thing. So you're not really saving any time or effort in doing it that way versus any other. So this is fine. So there you go. There's our solution. And notice, in this case, there wasn't this artificial feeling that I had of someone having to give me the homogeneous solutions. Right? This was a constant coefficient equation, so I could actually find the homogeneous solutions myself. So that's a big deal. Okay. Because if this is not a constant coefficient equation, then typically I will have to have someone give me those solutions. Okay. All right. Now, I will talk a little bit more later about, here we've ended up with a type of equation that is a little maybe nastier than you got to see in the previous examples where the right hand side had characteristic form, so we could use undetermined coefficients or key identities. So we ended up with something that's a little bit nastier. So there are some questions about the interval of definition of a thing like this. Right? So this is certainly a thing to pay attention to, because, like I said, this sort of thing didn't really happen previously. But so I'll show what sorts of things you could do to kind of pick out what the interval of definition is here for this, right? So ultimately, since you're taking the absolute value here, you're going to be avoiding the places where cosine t is 0. So in order to talk about, and of course this is going to split up into infinitely many pieces, so you would want to avoid places where cosine t is 0. So once I give you, the initial data, you would have to pick the relevant interval that data fell in, right? Okay, so let's do another example before I talk about that, which is the following. So suppose t squared and t squared, suppose t and t squared minus 1 form a fundamental solution set to the equation 1 plus t squared times y double prime minus 2t times y prime plus 2 times y is equal to 1 plus t squared squared e to the t. Find a general solution to this equation. Okay. So, I should correct this a little bit. So this is not exactly what I want. So form a fundamental solution set to the associated homogeneous equation to this. So t and t squared, right, t and t squared form a fundamental solution set to the equation 1 plus t squared y double prime minus 2ty prime plus 2y is equal to 0. So they don't solve this, they solve this, the associated homogeneous equation. Okay. All right. So I want to use that fact to find a general solution to this equation. Now, although, as I mentioned, these coefficient functions do not explicitly show up in my formula for variation of parameters, nevertheless, the entire calculations, all the calculations that I do, assume that the equation is in this form. Well, this equation, definitely variable coefficients. There's no surprise there. So the second I look at this, I'm like, yep, variable coefficients. So clearly I got to use variation of parameters. But this is not in this form. So I need to put it in that form. So let's divide through by 1 plus t squared. So this implies that the equation becomes y double prime minus 2t over 1 plus t squared times y prime plus 2 over 1 plus t squared times y is equal to 1 plus t squared. I'm dividing through. I have 1 plus t squared squared here, so I just get 1 plus t squared e to the t. Okay. All right, so I'm finding a general solution to this equation. Now, these solved, and they were a fundamental solution set, so they're linearly independent. These two solved the associated homogeneous equation for this, so they solved the associated homogeneous equation for this thing. Okay. Let's label, so y1, if y1 of t is t, and y2 of t is t squared minus 1, then the homogeneous solution is c1 t plus c2 times t squared minus 1. Okay. So variation of parameters, of course, allows me to find the particular solution to this thing. So what is the particular solution to this? Well, the particular solution is going to be u1 of t, y1 of t, plus u2 of t, y2 of t, where u1 and u2 are determined by those variation of parameters formulas, right? Just to remind you, there they are. Now, I found y1 and y2, or rather I was given y1 and y2 directly. I know what my f is, right? Remember, be careful here. This is my f, not the thing I started with. Because now this is in normal form, if you want to call it that. This is like linear normal form for a variable coefficient second order equation. So now f of t is 1 plus t squared e to the t. So we've got f, we've got y1, y2. We need to compute the Wronskian of y1 and y2. So let's do that real quickly. So, so what's the Wronskian of y1, y2 of t? This is y1 times y2 prime minus y2 times y1 prime. So this is y1, which is t, times y2 prime, which is 2t, right, minus y2, which is t squared minus 1, times y1 prime, which is 1. So what is this? This is 2t squared minus t squared plus 1. So this is t squared plus 1. Oh, I went off the page slightly. There we go. All right. So my Wronskian is t squared plus 1. y1 is t. y2 is t squared minus 1. F of t is 1 plus t squared e to the t. So let's see how this factors in. So then u1 of t is minus the integral of y2 of t f of t over the Wronskian y1 y2 of t dt. So what is that? This is minus the integral of t squared minus 1, that's y2, times f of t, which is 1 plus t squared e to the t, divided by the Wronskian, which is 1 plus t squared dt. So these cancel. And so I'm left with minus the integral of t squared minus 1 e to the t dt. Okay. So what do I do here? How do I integrate this? Well, I have to use integration by parts here. That's not too bad. If you like, I could split this up so that I don't have this minus 1 hanging around. It's however you want to do this. Let's just split it up. So let's write this as this is minus the integral of t squared e to the t dt plus the integral of e to the t dt. All right, so that's easy enough to take care of. And let's do integration by parts on this one. So you know how to do integration by parts. You want the thing that is going to get simpler when you take its derivative to be the u, and you want the thing that's going to typically you're just happy to be able to compute the dv term, right? So if I let u be t squared, right, then du is 2t dt. And if dv is e to the t dt, then v is e to the t. So we're happy with that. So how do I do integration by parts? This would be minus, this is going to be u times v, so that's t squared e to the t, minus the integral of v du, so that's 2 times t e to the t dt. And that's plus this integral, which is just e to the t, right? Plus c. If you like, I can add that in, or I can just use the fact that that's already taken care of from the homogeneous part. So I'm just going to write it like this. Again, I have to use integration by parts here. That's not too terrible. So this is minus t squared e to the t plus 2 times the integral of t e to the t dt plus e to the t. Here, what do I get here? I want to do the same thing, right? So I would, let's just write out integration by parts here. So u is t, and the du is dt, and dv is e to the t, and so v is, e to the t dt, and so v is e to the t. So writing out integration by parts again, this is minus t squared e to the t plus 2 times u times v, which is t e to the t, minus the integral of v du, so that's e to the t dt, plus e to the t. So this is minus t squared e to the t plus 2t e to the t minus 2 e to the t plus e to the t, so that's minus e to the t. There we go. Now, we could have done this in a more efficient way by just including everything. It doesn't really matter. It's the same thing. All right, so there's our u1 here. What about u2? So using my formula here, this is the integral of y1 of t f of t over the Wronskian
of y1, y2 dt. So y1 is just t. So this is the integral of t times 1 plus t squared e to the t over 1 plus t squared dt. So those cancel, and I'm left with the integral of t e to the t dt. Again, I can do this by parts here. So if I do this by parts quickly, this would be t e to the t minus e to the t, right? This is e to the t times t minus 1. Right. Okay. All right. And so so this is u1, this is u2. So our particular solution, so y is p of t, is minus t squared e to the t plus 2t e to the t minus e to the t times y1, which is t, plus e to the t times t minus 1 times y2, which is t squared minus 1. Of course, I could factor out an e to the t here, and I can also factor this as, this is like 1, this is like minus t minus 1 squared, right? So if you like, maybe I'll do that. So this is like minus e to the t times t. So minus t e to the t times t minus 1 squared plus e to the t times t minus 1 times t squared minus 1. That is what I get here. And then the general solution to the equation that I started with is the homogeneous part plus particular solution. Well, recall the homogeneous part is just c1y1 plus c2y2, right? So this is c1 y1, which is just t, plus c2 times t squared minus 1, plus particular solution, which is this thing. So plus, we'll say minus t e to the t times t squared, or sorry, t minus 1 squared, plus e to the t times t minus 1 times t squared minus 1. There it is. Okay. So that's how this goes. Now, as I just showed, this is when you have an equation that is variable coefficients in this form, it's not sufficient to just start going. You have to put it into this normal form, because I'm assuming in this whole process that the equation looks like this. So even though the a1 of t and a2 of t do not directly show up in the solution formula, it is important that it be in this form. So for instance, going back to show you, notice the 2t, the minus 2t over 1 plus t squared and the 2 over 1 plus t squared don't show up directly in the formula, but they're there hiding. In fact, the fact that a1 and a2 are equal to those things is what gives you the y1 and y2. Now, in this case, we were just straight up told that that those two were a fundamental solution set. This is typically how it's going to go if you actually have variable coefficients. So on one hand, right? If variable coefficients show up anywhere in a higher order equation, you know you have to use variation of parameters because there's nothing else in this course that will let you solve it. Okay. And in that case, of course, you will be told what some fundamental solutions are because you are not going to have the tools to be able to find them yourself. So you will have to be told. But it's important to see that that's not the only time you'll use variation of parameters. You will also use it when you can't use undetermined coefficients or key identities because the right-hand side is not in characteristic form. Okay, so that's these are the two most important cases. Of course, I've already told you you can always use variation of parameters if you really want to, but typically that's not advised just because it takes something that's an easier problem and makes it more complicated. Okay, so that's pretty much it for variable coefficient stuff. That's more or less all I wanted to say about it right now. So I am going to do a tie-in with what are called Green's functions that will kind of illustrate what it is that's going on with all this stuff, but I won't do that. I'll do that as kind of an addendum later. I think I'll probably do that after we talk about Laplace transforms. So I'll kind of have one big sort of like wrap-up lecture talking about Green's functions. So I'll kind of leave those for a little bit. Okay, so that's that for variable coefficients problems. So then the last thing I wanted to do before we get to Laplace transforms has to do with applications. So this is Chapter 2, Section 8, Applications. So just like in Chapter 1, right? So in Chapter 1, when we said applications, we really applied it to like a single type of problem, which was one of these tank problems, right? So a tank is being filled with some solution and setting up a first order differential equation to solve, for some quantity or to answer some question. Here in the applications problem, the primary thing we're going to be interested in are mass spring systems, okay, or spring mass systems. So in the context of higher order equations, specifically second order equations, when we say an application problem, typically what we mean is a spring mass system. Okay, so what is the setup? So imagine here's like the ceiling, we'll say. Okay, and from the ceiling, I have a spring. Okay, so I have a spring. This spring has like some initial position. When we talk about the position of the spring, what we're tracking is this end of the spring. Okay. So we'll call this our initial position, our initial height. We're tracking it in this direction, the height, so we'll call this y naught. That's our initial position here. Okay. Now, if I take this spring and I attach a mass to it, right? Well, you know what's going to happen, right? So if this spring is like a little hook on the end, and I put some sort of weight on it, right? I attach some mass to it, then this spring is going to stretch, right? It's going to be displaced some amount. So here is the spring after I've attached this mass to it. Okay. So then the same end of the spring has now been stretched some amount. But now, of course, I don't like put the spring on and it's bouncing around and I try to measure it. I don't put the mass on and then the spring is like bouncing around and I'm trying to measure it. What's happening is I attach the mass. Okay, I attach the mass and then I wait for the spring to stop moving so that this is now at a rest. This is the resting position or resting height. That's y sub r. Okay. So then this distance, right, is how much this spring is displaced by attaching some given mass to it. So one of the key pieces of information that you'll typically be given in a problem involving this is one of the key ways that a spring will be described to you is, all right, I have some spring, and I'm told that when I attach a 10 kilogram mass to the spring is displaced some amount. Okay, that tells me something about the spring. Okay, so this displacement amount is exactly that thing. Now, in general, the behavior that we're going to be modeling with this is to impart we have some initial position and then some initial velocity. That is, I move this spring and I let it go, right? And I want to know what is the position. I want to track this position at some generic time t. Okay, well, in that case, this thing is going to be bouncing around. Let's say it has bounced some amount after I've let it go, and at time t, right, the snapshot has me looking at this thing here. Right, there's my height. This is my y of t. Okay. How can I model this situation? So I use a few things here. The first thing I'm going to say is that basically I want to use, Newton. F equals ma, right? Where F is, we'll call this like the total forces acting on this system, right? M is going to be the mass of the mass or weight that I attach to this thing, and A is the acceleration, of course. Now, if y is tracking the position of this thing, right? Then acceleration, if y is position, then velocity is going to be y prime, and acceleration is going to be y double prime. Rewriting this in the other direction, this gives me y, or my double prime is equal to f sub total. And what is the total amount of forces? So here's what I'm going to do. I'm going to rewrite this slightly as I can write this amount of forces acting on the system as a sum. Okay, what are some of the forces? Right, so you may be looking at this thing and thinking of a couple already. If I've attached this to the ceiling, right, then clearly a force acting on this is gravitational force, right? So under most normal situations, so I have like gravitational force. Okay, what else? What other forces could be acting on this thing? Well, so added to this gravitational force, there could also be the force coming from the spring itself, right? So there's a lot going on with the spring. There's a lot of, if you've ever bought springs for buttons, say for like an arcade machine, right? Then you'll know that you can't just buy any spring you want to unless you want your buttons to be super duper stiff, right? If you want your buttons to be more easily pressable, then you want to buy springs having a certain force, right, associated with them, so you can get what are called like 60-gram springs, or if you want to train to be a true gorilla, you could get 200-gram springs if you want to destroy your fingers. So you could get springs that require much more force to actuate the button, right? So the spring force matters here. What else? Right? There's the damping force. What does that mean? Well, there's just the force inherent from where I have this thing hung, right? It's like the air in the room, right? Or maybe I'm doing this underwater, right? Um, so I have force coming from the medium, right? You can think of like the medium that this whole situation sits in. And then in addition to that, I have any other kind of external forces that are arising from, say, I mean, there's a number of things I could have here as a literal forcing function or forcing mechanism. So I'm not going to try to exhaustively list those, but there's basically any other external force here is taken care of by this last term. And so this is my model. And of course, it's this term on the left. It's the fact that F equals ma, where a is acceleration, that tells me this is a second order problem, right? I'm not going to be able to model this with purely a first order differential equation. I'm going to have to, this is going to be a second order equation if the thing that I'm modeling is position here, right? Okay, so there it is. Now, as I mentioned before, the point in this course is not to trick you with units. So basically, you will be given units in the proper form that you need to use them in. I'm not going to have you converting units or anything, so you don't need to memorize any unit conversions or look up any unit conversions in tables or anything like that. This is purely going to be, this is purely going to be in as usable a form as possible. You're not going to have to do much with the unit. So in this section, there's a little blurb to remind you. I'm just reading off the section. So in CGS units, length is given in centimeters, time in seconds, mass in grams, force in dynes, where 1 dyne is 1 gram centimeter per second squared. Maybe I'll write that out. Okay, so some refreshers. So some refreshers on units. So in CGS, units in length is centimeters. Time is in seconds. Mass in grams. And force is in dynes. And 1 dyne is equal to 1 gram centimeter per second squared. And in MKS, length is meters. Time is seconds. Mass is in kilograms. And force is in newtons, where 1 newton is equal to 1 kilogram meter per second squared. And then lastly, in imperial, length is in feet. Time is in seconds. Mass is in slugs, which is abbreviated SL. And force is in pounds. Where 1 pound is equal to 1 slug foot per second squared. Now, again, I'm writing this out for completion's sake. This is just so that when you see these units, you're not too confused. But the point is that in all these problems, you are going to be given units that are usable. You're not going to have to focus too much on how to deal with these. Okay. So I have this model. Here's my equation, and I want to see what each of these things look like. I want to see what each of these things look like. So what about this gravitational force? What is that? Well, this is just that downward weight of the mass, right? So this is just that downward weight of the mass, and so the gravitational force is minus mg. M is the mass of attached object, and g is what? G is 9.8 meters per second squared, right? If you're in MKS units, or 980 centimeters per second squared in CGS units, or 32 feet per second squared in imperial units. So this is the gravitational constant. This is our uniform gravitational acceleration that we're accustomed to on Earth. So there it is. All right. So that is the gravitational force. Okay. What about the spring force? Well, the spring force is minus k times y minus y naught. What is this? This is displacement of spring. Now, what did you just see here? Right? What is this? What's the k? I haven't said what k is. There's a reason why I used k. Where have you seen something like this? K times displacement. This is Hooke's law. This is just Hooke's law rewritten, reformed in terms of our problem, where k is the spring constant for the spring in question. Now, typically, the way that you arrive at k is not, typically this is not given to you directly, right? So typically you're not said, okay, consider a spring that has spring constant k equals to, 2.78. That's not how it's done. Typically, you will have to find the spring constant from other relevant info. Okay, so the most common way in which this is done is to note in the situation described that when there's no external force and the mass has some rest position that we were calling y sub r in our, we called the rest position y sub r here, then at that rest position, the gravitational force and the spring force cancel out. Okay. Well, think about that, right? Think about that physically. I attach mass to this thing, right? Gravitational force causes this thing to stretch, but eventually, right, it comes to a rest. It comes to a rest because of the force in the spring. So in the absence of other forces. At this rest position, these are in equilibrium, right? So the sum of the gravitational force and the spring force is 0. All right, but the gravitational force is, this is minus mg. I can move that to the other side. So this implies that mg is equal to k times the displacement. The reason I can replace this with an absolute value sign is because the resting position, we can assume that if we've oriented the picture in this way, that resting position, y sub r, is going to always be less than y naught, right? Because it's going to stretch it down, okay? And so I can actually replace this with this is the absolute value of y sub r minus y naught, or y naught minus y sub r, doesn't matter. So this relationship is extremely important. This is going to be typically, this is how you find k. So typically, this relationship is how you find k. What does this relationship say? M times g is equal to the spring constant k times the displacement yr minus y naught. So this displacement is the absolute value of yr minus y naught. It is this displacement to resting position from initial position. So I have initial position of spring, attached mass, it comes to a rest. That displacement is typically something, that's typically a quantity that I'm actually given in these problems. Okay. All right, so this is how I find that k. All right, and my spring force, remember I said, is this thing. Okay. We have another force to talk about, actually a couple more. There's the damping force. The damping force is typically modeled minus c, some constant, times y prime. And this c is called the damping coefficient. Now, this damping coefficient is typically also not given to you. You would have to find it. How would you find it? Typically, C is found by being given the magnitude of the damping force at some time, or at some velocity or speed. So since the absolute value of F damp is like the absolute value of C, and this damping coefficient C is positive typically. Or at least non-negative, I should say. This absolute value of the damping force is the absolute value of C times absolute value of y prime, so that's the speed. So if I tell you the magnitude of the damping force and the speed, then I can tell you what C is. Okay? So that's how that goes. All right. Okay, and so this is my damping force. And the external force we leave to later. That's going to be some function of t that I'll call the external force at t. Okay. And so putting all of those things together, I go from my double prime is equal to the gravitational force plus the spring force plus the damping force plus the external force. Well, notice all of these had minus signs in front of them, so we had minus c y prime we had minus k y to y minus y naught, then minus mg here. So what thing do I get putting all these things together? Putting all these things together, what I'm looking for is the actual displacement, which is, so if I let h of t be the displacement, let's go back to my picture. So this is y of t. If really what I care about, instead of the displacement from initial, I really only care about displacement once the weight is attached. So really, this is the thing I care about, and I call that thing h of t. Well, if that thing is h of t, what have I done there? Really, I've just subtracted off, right, the y sub r. And so if that's the case, then y sub t is really y sub r plus h of t, so that h of t is y minus y sub r. And so what I do is I set up a differential equation for h instead. This allows me to combine these terms into the following. So the resulting differential equation is m h double prime plus c h prime plus k h is equal to this external force. This is my general applications equation for a spring mass system. Okay. So this is going to be the equation that models this exact situation, and so this is going to be the thing that I refer to for all, whenever I'm asked a question about a spring mass system, it's going to be this that I refer to. Okay. All right, so that is that. So I think that's all for today. So I will see you all tomorrow. We'll finish this application stuff. All right.